Yeah, thank you, Win, for the introduction. Hello, everybody. As Win says, my name is Hui Wan. I'm at the PNNL, and I'm an atmosphere model developer. Today, on behalf of all the colleagues listed on the title slide, I would like to give you a overview of the a new funded project. And I know many of you in the audience are familiar with SciDAC, but just in case there are new colleagues, I wanted to briefly mention that SciDAC stands for Scientific Discovery Through Advanced Computing. This is a program under DOE's Office of Science, which has been funding research for more than 20 years. SciDAC projects typically have 5-year life cycles, and then the program includes collaborations between DOE's advanced scientific computing research and other research programs like BER, BES, high energy physics, etc. The BER ASCR partnership was recompeted last year. We are now in the 5th instantiation of the BER ASCR partnership. SciDAC projects by design are collaborative basic research efforts that have to involve physical scientists, computational scientists, and computer scientists. And this specific project I'm introducing to you today has the title Physical Accurate and Efficient Atmosphere and Surface Coupling Across Scales. This is a collaboration among 4 DOE labs, 3 universities, plus a partner from industry. Our scope, described in one short sentence, is to develop new algorithms for numerical process coupling in E3SM, especially in the atmosphere component. Our ultimate goal is to contribute to the improvement of numerical accuracy and computational efficiency of E3SM's multi-decadal climate predictions. In the presentation today, I thought I would describe our project objectives and provide an overview of the tasks so that hopefully this can facilitate the coordination and collaboration between our projects and the E3SM team. So regarding the scope, I thought I'd first clarify what we mean by numerical process coupling. To this audience, there is no need to explain that E3SM and its component models are all multi-process models that have a lot of interacting subcomponents. By numerical process coupling, we are referring to this question that after state-of-the-art representations of individual processes have been developed by the corresponding experts, what numerical algorithms should we use to assemble all those different pieces into a full, coherent, and performant model? Our project focuses mainly on time integration part of this question, but as you will see later, some tasks will unavoidably involve vertical discretization as well. For time integration, our primary focus is on reducing splitting errors. So let's take a moment and look at this a little schematic on the slide, and imagine that we need to couple together these 7 processes A, B, C, D, E, F, G. So for during each model time step, we have to decide how we calculate these processes. For example, do we calculate them all in parallel using the same atmospheric state, or do we calculate them one after another with the output from one process being provided as an input to the next process, or we do something that is a combination of these two? It has been shown in the past years that splitting errors have been the big cause of some significant inconvenience in E3SM development. For example, many of our atmosphere model developers are familiar with the fact that our model results are highly sensitive to the model time step delta t and then the vertical resolution delta z. For example, with E3SM V1 atmosphere model, at 1 degree horizontal resolution, if we reduce the model time step from the default value to 1/6 of the default, then we would see in terms of annual averages, total cloud fraction decreases on the order between 20% to 50% in rather large areas in the subtropical ocean. And if it was also noticed that in Ethereum v1, when the vertical resolution was decreased from 30 layers, was increased from the 30 layers to 72 layers, the global mean annual mean dust lifetime also decreased substantially. For these two examples shown here, we have been able to show that these sensitivities all have to do with splitting errors that are caused by the time integration algorithm. Considering that EAM is expected to be evaluated and used at a wide range of horizontal resolutions, when the model developers and users use these different resolutions, there is this practical question how we should choose delta t or delta z. If the sensitivities shown here are not addressed, then when going to a different resolution, the developers will have to either change delta t or delta z and then retune the model parameters, or they will have to try to avoid the retuning by living with fixed delta t or delta z, neither of which are desirable scenarios. In the previous round of SciDAC, we were able to show that the splitting errors can be identified, understood, and substantially reduced. For example, again, for these two examples, we were able to make rather simple changes in the atmosphere model and then substantially reduce the time step sensitivities in subtropical low cloud fractions and the resolution sensitivity of a dust life cycle. But due to time constraint, we only scratched the surface of the big coupling problem, leaving many sensitivities and coupling errors unaddressed. So this new round of SciDAC, this new project is providing us with an opportunity to look at this coupling problem at a deeper level and in a more systematic manner. By more systematic, we mean that the new project will address numerical coupling challenges at multiple levels of ETHRSM's model hierarchy. So within the atmosphere, for example, there are coupling questions and the coupling problems at the so-called atmosphere driver level, but then also such problems and challenges within parameterizations. And since EAM is a component of ETHRSM, the atmosphere is coupled to the Earth's surface, and then there are known issues there too. In this project, we have designed a total of 5 tasks to address all these kind of coupling errors or coupling problems at these different levels. In addition, we are developing new visual analytics tools to help analyze the model results and hopefully speed up the development. And last but not least, we are devoting some dedicated staff and dedicated time to help our project remain closely connected to the ETHRSM project. The overall objectives of the project are the following. At EAM's workhorse resolutions, we aim at reducing the time integration errors to a level below the spatial resolution errors and model formulation errors. And anticipating that a wide range of horizontal resolutions will be used by the atmosphere model, we aim at improving the solution convergence with respect to time step and vertical resolution for EAM's cloud microphysics and turbulence parameterizations. Overall, we are aiming at delivering a version of EAM that allows the developers and users to choose the step size and the vertical resolution consistent with their horizontal resolution and based on the underlying physics. So that was an overview of the project as a whole. So in the next minutes, I would like to give you an overview of the specific tasks and what we plan to do under each task. Again, the purpose here is to hopefully facilitate the collaboration with the E3SM team. Task 1.1 on our project is about process coupling in the atmosphere. We have two co-leads, one being myself, the other being Chris Vogel, who is an applied mathematician at Lawrence Livermore National Lab. The scope of this task is to reorganize process groups and their coupling at the atmosphere driver level. For the colleagues in the audience who are familiar with the EAM code, I have this schematic here showing the so-called physics driver subroutines, TFIS AC and TFIS BC, which cause a series of parameterizations or parameterization groups. What we mean by reorganized process groups and their coupling is that we will break apart quite a few of those white boxes, reassemble them differently, and then change the sequence of calculation in this view and use different splitting and coupling methods. The details of the revisions that we will make will be guided by the following pieces of information. First, very importantly, the physics. We will identify the main sources and sinks in the prognostic equations of the model and quantify their characteristic timescales. And we will quantify the model sensitivities to revisions in process coupling and assess the impact. From the math side, we recently developed a theoretical error analysis framework that allows for process level analysis of the sources of splitting error. We will use that method to analyze the current methods, coupling methods used in EAM, and also design new methods, making use of fast math expertise on time integration. And we will also, of course, estimate the computational cost and try to achieve a good trade-off between cost and accuracy. We plan to make code changes in E3SM v2 to start with, and then v3 when it is released. And unlike the previous round of SciDAC, our code changes this time are expected to be rather intrusive. We understand that the Fortran code will be replaced by the C++ code in v4, but we hope that the things we learn about the physics and the numerics using v2, v3 will provide useful information for the v4 model developers. So the next task on our project is called atmosphere surface coupling. The two co-leads are Xubing Zheng from University of Arizona and Carol Woodward, who is an applied mathematician at Lawrence Livermore National Lab. This task aims at addressing two challenges. One is the numerical instabilities that have been noticed in the E3SM simulations in near surface atmospheric quantities, as shown by this top right figure here from Sean Santos. The second subtask in this task is to assess and address the so-called surface layer gray zone problem. So this problem that we refer to as surface layer gray zone has to do with the fact that the so-called atmospheric surface layer, which is the bottom of an atmospheric column that touches the surface, typically has the depth on the order of about 100 meters. In the older days, when the model resolutions were coarse, this 100 meters would fall within the bottom layer in the atmosphere, and the model formulation and the numerical methods were designed to accommodate that situation. But since EtherSM V1, we are now having much thinner layers in the atmosphere. Now for the altitude range covered by the surface layer, we have about 3 layers, and then the bottom layer is can even be as can even be lower than the canopy height in some situations. So what does this mean to our model? So are there model assumptions and formulations and numerical methods that uh, are no longer valid? So these are things that we want to look into and then understand what the impacts or what the implications are for in terms of designing process coupling algorithms. So in this task, we will uh, um, look into the non-physical oscillations, try to identify the root cause of this problem, and then probably revise the coupling between the surface and the turbulence parameterization. And as for the gray zone problem, we plan to clarify and revisit model assumptions, identify inconsistencies, assess the impact, and then propose possible solutions. The next task on the project has to do with cloud microphysics. This is co-led by Sean Santos at PNNL and Carol Woodward at Lawrence Livermore National Lab. The scope of this task is to develop new spatial temporal discretization methods for the coupling of local and non-local cloud microphysics processes. By local process, we mean the processes like condensation, vapor deposition, collision coalescence processes that lead to rain formation. By non-local processes, we mean the sedimentation of the hydrometeors and then the possible presence of strong updraft and downdraft in within clouds that provide the environment for the local processes to happen. So the colleagues who have worked with EtherSM's cloud microphysics code probably know that there are a lot of so-called conservation checks in the code that are actually fixers for avoiding negative tracer concentrations. And also, although the microphysics code has gone through versions like MG1, MG2, P3, the rain snow formation processes and the hydrometeor sedimentation processes are sequentially split in the numerical algorithm, which prevents the rain or snow to interact with the cloud layers that they fall through. And then deep convection, which involves updraft, uh, then causes additional challenges when we want to describe detailed microphysical processes. So the planned work is to write a new cloud microphysics driver for the P3 microphysics package. And during that rewrite, a key task is to implement tighter coupling between the local and non-local processes. We plan to explore a range of spatial temporal discretization methods, for example, multi-rate time integrators from the fastmass sundials package and semi-Lagrangian methods, etc. The code is being written in C++. The next task on the project is about improving discretization for boundary layer turbulence. This is co-led by Vince Larson at University of Wisconsin-Milwaukee and Anne Almgren, who is a senior mathematician at Berkeley Lab. The scope of this task is to develop new strategies based on finite volume methods to address challenges associated with very sharp vertical gradients. For example, the big jumps of atmospheric quantities that we see at the top of the stratocumulus layers. So why are we interested in finite volume methods? This is because finite volume discretizations typically have a starting point, which is the integral form of the equations. The integral equations are a more fundamental representation of the underlying physics. And because the finite volume methods are designed to handle discontinuities, the methods will not break down when we have such sharp gradients. And also in the previous round of SciDAC, we have made some explorations and obtained encouraging results, which shows that by introducing some finite volume methods, we could substantially reduce the need for clipping for some of the prognostic variables within club. So in this new round of SciDAC, we would like to explore finite volume methods for vertical and for the vertical discretization in club, and we will use single column simulations for a large part of the development. And then when the methods are mature, then we will implement and test in E3SM. One comment to make here is that at a given resolution, a FV-based discretization might turn out to be more expensive than the current finite difference methods, but we expect that the finite volume approach has the chance of providing substantially improved solution quality, and it also gives a starting point for further optimization of the computational performance. The next task on this project is called coupling issues in PDE-ML hybrid systems. This is co-led by Guang Zhang from UCSD and Panos Stinis from PNNL. So the idea here is that because we look a lot into the process interactions, we might be able to use our understanding of the physics and the process interactions and the coupling algorithms to help identify root causes of the commonly encountered instability problems when machine learning based moist physics parameterizations are introduced to global atmospheric models. So for this task, we will use a version of CAM5, which has neural network-based moist physics parameterizations, and do sensitivity experiments between the PDE-based simulations and the PDE-ML hybrid simulations to explore the causes of such instabilities and explore possible revisions to either the process coupling or the construction of the machine learning based parameterizations to help alleviate this problem. So this task will make use of tools and insights from the other tasks. And we also expect that during this task, we will learn more about the physics, therefore provide useful insight and contributions to other tasks on the project. So these were the model development tasks we have on this project. And to facilitate the model development, we are working with colleagues from Kitware to develop new visualization tools. So many of our modelers know that if we want to do process level evaluation, the post-processing and the visualization process can be rather tedious. But in the meantime, DOE leadership computing facilities have made available modern visualization and tools. Unfortunately, we have not used those tools a lot, at least for the atmosphere model development. So in this task, we plan to develop a easy to use user interface for visualization tailored to the needs of the atmosphere developers. And also because we have some parameterization development or numerics work for parameterizations, we will develop visual analytics workflows for those too. So here is just a first example showing that with the colleagues who are experts of the visualization tool called ParaView has recently written a new reader for E3SM v2 so that ParaView can now present E3SM v2 output in ways that are intuitive for the atmosphere model developers. And as for integration with E3SM, we have Wu Yinlin and Jianfeng Li co-leading this task. The purpose really is to ensure that code developed in the project is compatible with the current and future versions of the E3SM code, and to make sure that we can incorporate our code improvements into E3SM's master branch in a timely manner. Hui Lin is acting as our project's liaison with E3SM, and we have team members who are now regularly participating in E3SM Phase 3 atmosphere groups bi-weekly meetings and the screen teams weekly meetings. We appreciate that the corresponding group leads gave us the permission to join the conversations. And as for the hands-on work of code integration, Jianfeng Li and Wu Yinling are playing key roles in integrating our code changes to E3SM. So that's pretty much everything I wanted to say in this presentation. My concluding remark is that this project is all about interactions between model components, about interactions between model developers, and the interactions between system scientists and applied mathematicians and computational scientists and computer scientists. So collaborations are definitely welcome. Please don't hesitate to contact us if you see an opportunity for us to chat. So that's all I have. Thank you.